closed loop control system from the Good morning, students. Now, in the previous session, we just discussed the calculations of gain margin and phase margin. In that topic, we just finished the gain margin calculations, how to find the gain margin. Now, we will see the how to find phase margin and what is the phase margin calculation. And after that, we will see how to find the closed loop control system stability from the plots or from the open loop transfer function frequency response is nothing but it may be Bode plot or polar plot, whatever it may be. Okay. Now, first we will see the phase margin calculations. Now, what is a phase margin? The phase margin, which is nothing but 180 degrees plus angle of open loop transfer function at omega gc. Angle of open loop transfer function at omega gc. Now, what is omega gc? The omega gc is the gain crossover frequency. Omega gc is nothing but gain crossover frequency. Gain crossover frequency. Now, what is the gain crossover frequency? This phase margin is calculated for an open loop transfer function, but this open loop transfer function angle is calculated at gain crossover frequency. What is a gain crossover frequency? Now, first we will see what is a gain crossover frequency. The gain crossover frequency is the frequency at which magnitude of the gain crossover frequency is the frequency at which magnitude of open loop transfer function which is equal to 1. The magnitude of open loop transfer function which is equal to 1, then you can get a frequency. That frequency is nothing but gain crossover frequency. And you know that when the open loop transfer function magnitude, is equal to 1, which means that it satisfies the magnitude condition. You know the link between open loop and closed loop control system, whether you should follow angle condition or you should follow magnitude condition or whether you should choose a point condition. Therefore, angle of open loop transfer function which is equal to 1, then that particular frequency is called as gain crossover frequency. Suppose if it is given in terms of dBs. So, if it is given in terms of dBs, then what happens? Now, 20 log magnitude of g of j omega which is equal to 20 log 1 base 10. Therefore, 20 log magnitude of g of j omega base 10. Now, the magnitude in terms of dB which is equal to 0 dB. If magnitude is exactly equal to 1, then that particular frequency is called as gain crossover frequency. Or if that magnitude is in terms of dB, then you can equate to 0 dB. Then that particular frequency is called as gain crossover frequency. Student, note down what is the gain crossover frequency. Gain crossover frequency is the frequency at which the magnitude of open loop transfer function is equal to 1 or the magnitude of open loop transfer function in terms of dB is equal to 0 dB. Then that particular frequency is called as gain crossover frequency. At gain crossover frequency, then if you measure at gain crossover frequency, if you measure the angle, and this is the phase margin now which is calculated for open loop transfer function, but which is at a gain crossover frequency, which is nothing but definitely there is a link between open loop and closed loop control system. Now, first you note down this definition, then this formulas, and after that we calculate how to find the gain crossover frequency and how to find the phase margin we will see. Okay, then we'll solve one question such that you can easily understand. Okay. Now, g of s, which is equal to 1 minus s by 1 plus s into 1 plus 2s. Then this is the open loop transfer function which is given to you, and he is asking to find the gain margin. G of s equal to 1 minus s by 1 plus s into 1 plus 2s. Then he is asking to find the gain margin. Okay. So, but here it is a phase margin. But gain margin calculations which we are already completed, then we will see the phase margin calculation. So, what is the phase margin? So, now first I replace s with j omega, g of j omega, which is equal to 1 minus j omega by 1 plus j omega into 1 plus j2 omega. Now this is g of j omega. And what is the phase margin? The phase margin, which is equal to 180 degrees plus angle of open loop transfer function. What is the angle of open loop transfer function? This is numerator, therefore plus tan inverse imaginary part by real part. Next, denominator minus tan inverse imaginary part by real part. Again, this is also denominator minus tan inverse imaginary part. Imaginary part here is 2 omega by 1. This is angle of open loop transfer function. This is the angle of open loop transfer function at at gain crossover frequency. This is the angle of open loop transfer function at gain crossover frequency. So at omega gc, at omega gc, at omega gc. But what is the gain crossover frequency, student? Now what is the gain crossover frequency? A gain crossover frequency is the frequency at which a magnitude of open loop transfer function is equal to 1. So what is the magnitude? A magnitude of open loop transfer function. The magnitude of open loop transfer function which is equal to, now see here, g of j omega. What is g of j omega? 1 minus j omega by 1 plus j omega, 1 plus j2 omega. Now this is g of j omega. Therefore, the magnitude of open loop transfer function. What is the magnitude of open loop transfer function? Now for this you can calculate the magnitude. Now what is the magnitude? Now square root of a square plus b square, square root of real part square plus imaginary part square, square root of real part square plus imaginary part square. Now this is the magnitude which is equal to 1. So when this magnitude which is equal to 1, now this particular frequency is called as gain crossover frequency, gain crossover frequency, gain crossover frequency. Now students, now if you substitute this one, now this 1 plus omega g square, 1 plus omega g square cancel, 1 plus 4 omega gc square equal to 1 under root. If you square both sides, 1 plus 4 omega gc square equal to 1, square both sides, 1 minus 1, 0, 4 omega gc square equal to 0. Therefore, omega gc which is equal to 0 radians per second. Now this is the gain crossover frequency. Just wait a second and this is a valid gain crossover frequency. You will cross check. Now how to cross check? The gain crossover frequency is the frequency at which the magnitude of open loop transfer function is equal to 1. You substitute this omega gc in the magnitude 1 plus 0, 1 plus 0, 1 plus 0, which is equal to 1. Therefore, at this particular frequency, magnitude is equal to 1, and that is a valid gain crossover frequency. This is the valid gain crossover frequency. Now, at that particular gain crossover frequency, then we want to find the phase margin. Now, see here, let us see here the phase margin. Now, the phase margin, which is equal to 180 degrees plus, what is the angle of open loop transfer function at omega gc? Now, this is omega gc is 0. Therefore, tan inverse 0 minus tan inverse 0 minus tan inverse 0. Therefore, tan inverse 0 is 0, 0, 0 degrees, 0 degrees, 0 degrees. Then finally, what is the phase margin? The phase margin, which is equal to 180 degrees plus 0 degrees, which is equal to 180 degrees. This is the phase margin. This is the way how to calculate the phase margin by considering the open loop transfer function. Okay, note down this one. Okay. Now, this is the way actually we are calculating the gain margin. Okay, we'll solve a few problems on this particular phase margin. Now, G of S, which is equal to 0.5 by S plus 1. Now, replace S equal to J omega, GR 0.5 by 1 plus J omega. Then what is the phase margin? 180 degrees plus angle of open loop transfer function. What is the angle of open loop transfer function? Denominator. So, minus tan inverse omega by 1. I want this this phase angle at gain crossover frequency. I want this angle at omega gc. Okay. So, what is omega gc? What is the gain crossover frequency? Now, we'll see what is gain crossover frequency. So, you know that the gain crossover frequency is the frequency, a magnitude which is equal to 1. What is G of j omega? G of j omega here is 0.5 by 1 plus j omega. 1 plus j omega. Now, magnitude of open loop transfer function which is equal to 1. What is the magnitude? 0.5 divided by square root of a square plus b square, which is equal to 1. When magnitude is equal to 1, this particular frequency is called as gain crossover frequency. Then whatever you are doing, cross multiplications or calculations and simplifications and all these things, you will not get the valid gain crossover frequency strength. Now, sir, why the previous problems are having a valid gain crossover frequency, but why this problem will not have a valid gain crossover frequency? The reason is, we will see the magnitude plot, right? Now, when omega equal to 0, what is the magnitude? The magnitude which is equal to 0.5 divided by square root of 1 plus 0, which is equal to 0.5. When omega equal to 1, what is the magnitude? The magnitude which is equal to 0.5 square root of 1 square plus 1 square, which is equal to 0.5 divided by root 2, which is equal to 0.35. And so on, and so on, and so on, when omega equal to infinity. So, you find for When omega equal to infinity, what happens? When omega equal to infinity, the magnitude is 0.5 square root of 1 plus infinity, something by infinity, which is equal to 0. Now the students, what you observed? You observed that as frequencies are changing from 0 to infinity, you substitute all the frequencies. You substitute all the frequencies from 0 to infinity, but you can get the maximum magnitude of how much? 0.5. But if you want the existence of the gain crossover frequency is the frequency when the magnitude is equal to 1. But your magnitude is maintained. Your magnitude is maintained. Your magnitude plot is maintained less than 1 for all the frequencies. For all the frequencies from 0 to infinity. I am substituting all the frequencies from 0 to infinity, but the magnitude plot is maintained less than 1. Then the gain crossover frequency. What is the gain crossover frequency? It will cross the gain of 1. It will cross the magnitude of 1. But you substitute all the frequencies. But your magnitude will not cross 1. Your gain will not cross 1. Then the gain crossover frequency does not exist. Therefore, the gain crossover frequency does not exist. And therefore, the phase margin is an unbounded value. The phase margin is unbounded. Whenever the gain crossover frequency does not existing, it is not a valid phase margin, and there is no link between open loop and closed loop control system. It does not existing practically. That is the reason why I am saying n number of times. While you are calculating the gain crossover frequency, or whether you are crossing the phase crossover frequency, you just cross check at that particular frequency magnitude is 1, or at that particular frequency phase angle is 180 degrees. Then only the valid gain crossover frequency, then only the valid phase crossover frequencies are existing. Otherwise, that gain margin, phase margin is invalid values, no link between open loop and closed loop control system. Okay, therefore note down this. Okay, now this is the way you calculate the phase margin. Okay, now let us solve one more problem. Now, G of S, which is equal to K by S into S plus, G of S equal to K by S into S plus 1. Now the question is, determine value of K to get phase margin 30 degrees. Now, G of S equal to K by S into S plus 1, determine value of K to get the phase margin 30 degrees. He is asking the value of K and to get the phase margin 30 degrees. Now see here, now G of J omega, same procedure you should follow. K divided by 0 plus J omega, 1 plus J omega. How to calculate the phase margin? Phase margin is 180 degrees plus, all are in denominator, therefore minus tan inverse imaginary part by real part minus tan inverse imaginary part by real part. Therefore, now this is at gain crossover frequency, at gain crossover frequency. Now phase margin phase margin which is equal to 180 degrees minus tan inverse infinity is 90 degrees minus tan inverse omega GC. Therefore, what is the phase margin? The phase margin which is equal to 180 minus 90, 90 degrees, 90 degrees minus tan inverse omega GC. This is the phase margin of a given open loop transfer function. But in the question is already mentioned the phase margin. What is the phase margin? The phase margin is 30 degrees. Is given already. So can I equate these two? This is the phase margin and this is also the phase margin of the same transfer functions. So can I equate to these two phase margins and I can get any relation? Yes. Therefore, 90 degrees minus tan inverse omega GC which is equal to 30 degrees. Therefore, tan inverse omega GC equal to 60 degrees. Therefore, omega GC which is equal to tan 60 is √3 radians per second. Now this is omega GC what we are getting. But in the question he is not asking omega GC. In the question he is asking determine the value of K. What is K? Am I not? Now I get here gain crossover frequency. But if the gain crossover frequency is not given, what is the procedure to calculate the gain crossover frequency? And this is the procedure to calculate the gain crossover frequency, right? What is G of j omega? G of j omega, which is nothing but K divided by 1 plus j omega, 0 plus j omega. This is G of j omega. But what is the gain crossover frequency? Gain crossover frequency is the frequency at which the magnitude of open loop transfer function which is equal to 1. Therefore, now you find how to find the gain crossover frequency. Now this is the procedure. Now magnitude, what is the magnitude? K divided by square root of a square plus b square, square root of a square plus b square, which is equal to 1. When the magnitude which is equal to 1, then this particular frequency is called as gain crossover frequency. This particular frequency is called as gain crossover frequency. Now the magnitude which is equal to 1, K which is equal to now omega GC into square root of 1 plus omega GC square. Now this is the magnitude which is equal to 1. When the magnitude which is equal to 1, that particular frequency is called as gain crossover frequency. Now I know gain crossover frequency. What is the gain crossover frequency here? The gain crossover frequency is √3. Can I substitute here? Therefore, K which is equal to √3 into square root of 1 plus √3 whole square, square root cancel, 3 plus 1, 4, under root of 4 is 2. So system gain K which is equal to 2√3. This is the value of K. To get the phase margin 30 degrees, the K value is 2√3. Note down, students. Okay. Now you know how to calculate the gain margin and you know how to calculate the phase margin and what is a valid gain margin and what is a valid phase margin. That is important rather than calculating all these parameters. Okay. But these gain margin and phase margin are calculated for a open loop transfer function. But based on this open loop transfer functions, Now, how to analyze the closed loop control system behavior is an important point here. Now, you know how to find the gain margin and you know how to find the phase margin. You know what is a valid gain margin and you know what is a valid phase margin. Now by taking a reference of, if the gain margin is exactly 0 dB, if the phase margin is exactly 0 degrees, this is margin for gain and this is margin for phase. This is the marginal for gain and this is the marginal for phase. If the phase margin is exactly 0 degrees, if the gain margin is exactly 0 dB, then this is a boundary, margin for gain and margin for phase. If the margin for gain is exactly 0 dB, margin for phase is exactly 0 degrees, then the closed loop control system is marginally stable. Then the closed loop control system is marginally stable. This is the margin for gain and margin for phase. But my system is not maintain a required gain margin and not maintain a required phase margin. If your gain margin is less than 0 dB, if your phase margin is less than 0 degrees, this is the negative value. This is also the negative value. It is a minimum boundaries, margins, but you are not maintaining a minimum required value, then the closed loop control system is unstable. My system is maintain a sufficient gain, sufficient phase. Now, if the gain margin is greater than 0 dB, if the phase margin is greater than 0 degrees, this is the positive value. This is also the positive value. Then the closed loop control system is stable. Now it produces a sufficient gain. It produces the sufficient phase. Then this is a closed loop control system is a stable, and this is unstable, and this is marginally stable. But these parameters are calculating for open loop transfer function, but I want to do the analysis of closed loop control system. This is the way the link between open loop and closed loop control system. Note on this. Okay. Now, so you find the gain margin and phase margin, and from that you decided the closed loop control system behavior. Now let us see here. Now let us just give one small example such that you can easily understand. This is one plot which is given to you. Now with this example, I hope you can easily understand. Now this is one plot which is a relation between magnitude of open loop transfer function. Now see the students here. This is one plot which is given to you. This is a relation between open loop transfer function phase angle in terms of degrees and open loop transfer function magnitudes. This is the magnitude of open loop transfer function in terms of dBs. Okay. Now here given magnitude in terms of dBs as well as phase angle in terms of degrees. Then he is asking, this is the open loop control system relation, but he is asking about what is the stability of the closed loop control system. This is the question what he is asking. Then how to find that? Then we can find like this. See here. Now this is 0 dB line. This is 0 dB line. So can I extend it this 0 dB? This is the 0 dB line. Now can I extend it this 0 dB line to the plat? The plat will touch at a particular frequency. Now when magnitude of open loop transfunction is equal to 0 dB, now this particular frequency is called as gain crossover frequency. I am not interested on the gain crossover frequency. What is the gain crossover frequency? Now what is the phase margin? Now let us see here. The phase margin, which is equal to 180 degrees plus angle of open loop transfer function yet gain crossover frequency. I am not interested on a gain crossover frequency. I am interested angle at gain crossover frequency. Now magnitude equal to 0 dB, then this is gain crossover frequency. Yet gain crossover frequency, what is the phase angle of an open loop transfer function? So yet gain crossover frequency, the phase angle of an open loop transfer function is how much? Minus 100 degrees. Therefore, then this is the value which is nothing but minus 100 degrees. And this is 180 degrees plus. Therefore, what is the phase margin? This is the phase margin. The phase margin which is equal to 180 minus 100, which is equal to 80 degrees. This is the phase margin. The phase margin is 80 degrees. Okay. So, but if you want to decide the stability, we require a gain margin also. What is the gain margin? Now, a gain margin is nothing but first we want to find magnitude of open loop transfer function. But what is the gain margin in terms of dB? The gain margin in terms of dB is nothing but, now first I want to tell you, gain margin, which is nothing but reciprocal of magnitude of open loop transfer function yet phase crossover frequency. This is in terms of magnitude. If I want in terms of dB, gain margin in terms of dB, which is equal to 1 by reciprocal means here minus 20 log magnitude of g of j omega at phase crossover frequency. This is the gain margin in terms of dBs. But I want a phase crossover frequency. What is the phase crossover frequency? See here. Phase crossover frequency is the frequency. Phase angle of an open loop transfer function equal to minus 180 degrees. This is a minus 180 degrees. If I extend it to the plat, when a phase angle equal to minus 180 degrees, this particular frequency is called as phase crossover frequency. I don't want a phase crossover frequency. Yet phase crossover frequency, I want magnitude. Or I want at phase crossover frequency, I want magnitude in terms of dB. This is in terms of dB. But already the options are given in terms of dBs. Therefore, yet phase crossover frequency, what is the magnitude? Yet phase crossover frequency, the magnitude is, yet phase crossover frequency, the magnitude is minus 20 dB. Therefore, this is the open loop transfer function magnitude in terms of dB. Therefore, this is minus 20 dB. But a gain margin is nothing but reciprocal. Now, because of the reciprocal, here is a minus sign. Therefore, what is the gain margin in terms of dB? Is nothing but plus 20 dB. Now, most of the students, you are missing this negative sign. No, you have to be kept this negative sign if the given in terms of dBs. If it is not in terms of dBs, you straight over take this value. It's not a problem. Okay. But this is given in terms of dBs. Therefore, there is a negative sign here. So, gain margin is equal to plus 20 dB and phase margin equal to 80 degrees. Therefore, this is the positive value and this is also the gain margin 20 dB. This is also the positive value. Therefore, both are positive. Then the closed loop control system is stable. Therefore, finally, what is the conclusion? Gain margin is positive. Phase margin is positive. Therefore, closed loop control system is stable because gain margin is we can get a positive value and a phase margin we can get positive value. Okay. This is the way how to calculate the gain margin and phase margin from the plat. This may be a Bode plat. is a magnitude in terms of dB, phase angle in terms of degrees. Note down, very, very important. Okay, but sometimes he is giving magnitude plot separately and he may give the phase plot also separately. Now in such a situation, then how we can calculate? Now see here. Now he is given magnitude plot separately and phase plot separately, because both a magnitude plot and both a phase plot. Now he is giving separately. Now see here, this is both a magnitude plot in terms of dB. This is both a phase plot in terms of degrees. Now he is given magnitude plot as well as phase plot. This is magnitude plot and this is a phase plot. Then he is asking, this is open loop transfer function magnitudes and this is open loop transfer function phase angles. Then he is asking to find the closed loop control system stability. This is the open loop transfer function. Okay, don't confuse. This is the open loop transfer function. Angle of, this is angle of G of j omega in terms of degrees. This is magnitude of G of j omega in terms of dB. Okay. So in the same problem, same situation, same conditions, you just see here. Now this is 0 dB line. So when magnitude is equal to 0 dB, this particular frequency is called as gain crossover frequency. So this gain crossover frequency you should extend it. Then it will touch at a particular point on the phase angle. Now at this particular gain crossover frequency, what is the phase? The phase is minus 150 degrees. Therefore, yet gain crossover frequency, the phase angle is, yet gain crossover frequency, the phase angle, yet gain crossover frequency, the phase angle is 150 degrees. Therefore, this is minus 150 degrees. Therefore, what is the phase margin? 180 minus 150, 30 degrees, which is a positive value. So, now similarly, at the same manner, now phase angle equal to minus 180 degrees. When phase angle equal to minus 180 degrees, then this particular frequency is called as gain crossover frequency, phase crossover frequency. When a phase angle equal to minus 180 degrees, this particular frequency is called as phase crossover frequency. Now you extended this phase crossover frequency to the magnitude plot. Then it will touch at a particular point. Now, yet phase crossover frequency, what is the magnitude? Yet phase crossover frequency, the magnitude in terms of dB is minus 10. Therefore, now at phase cross of frequency, what is the magnitude? At phase cross of frequency, the magnitude which is equal to minus 10 dB. This is minus 10 dB. But a gain margin is nothing but the reciprocal. The reciprocal is nothing but minus plus. Now this is nothing but plus 10 dB. Now the closed loop control system is stable because the gain margin is a positive value and a phase margin is also positive. And the system is stable. Not only that, in this particular case, then you may also find one more relation here. Now this is omega GC, this is omega PC, and this is the phase, this is the frequency axis. The frequencies are changing from 0 to infinity, 0 to infinity. In that, this is GC and this is PC. What is the relation between gain cross of frequency and phase cross of frequency? If the closed loop control system is stable, the gain cross of frequency is less than phase cross of frequency. If gain cross of frequency is less than the phase cross of frequency, then the closed loop control system is stable. This is both a magnitude plot and this is both a phase plot. Then you can decide at the stability of the closed loop control system. No doubt. Okay. Now the problem is like this. Now let us see, for example, now the problem may be like this. You just see here. Now when magnitude equal to 0 dB, then this particular frequency is called as gain crossover frequency. At gain crossover frequency, what is the phase angle? At gain crossover frequency, the phase angle is exactly minus 180 degrees. At gain crossover frequency, the phase angle is exactly minus 180 degrees. Exactly minus 180 degrees. Then 180 degrees minus 180 degrees, 0 degrees. Exactly. Now, similarly, now when phase angle equal to minus 180 degrees, then this particular frequency is called as phase crossover frequency. Now, at phase crossover frequency, what is the magnitude? Magnitude is exactly 0 dB. So, at phase crossover frequency, the magnitude is, this is 0. Therefore, which is nothing but 0 dB. So, at phase crossover frequency, this is exactly 0 dB. Therefore, gain margin is 0 dB. Phase margin is 0 degrees. Therefore, closed loop control system is marginally stable because gain margin is exactly 0 dB phase margin is exactly 0 degrees. And gain cross of frequency, phase cross of frequency, both are exactly same. Gain cross of frequency equal phase cross of frequency, closed loop control system is stable.